right, guys, so we're going to be looking at how to find the area under a curve. That's what integration does for us. It finds the area under the curve. So this first one, this definition here, it says the definite integral as the area of a region. If a function is continuous, that means it can't have any breaks in it, and it's non-negative, that means it's always above the x-axis. On the closed interval, that just means we have stopping points of a and b. Then the area of the region bounded by the graph of the function, the x-axis, and the vertical lines x equals a and x equals b is given by this formula. The area is going to be equal to the integral from a to b, where a is on the left, b is on the right. You might want to fill that in. So this is your left value, and this is your right value. This is your function, and then that just shows we're integrating with respect to x. All right, so let's look at this first one. So right here, that's going to be our function. See how that's in that position? That's our function. So in this case, f of x equals 4. Well, f of x is the same thing as y. So do you know what the graph of y equals 4 looks like? Yeah, it's just going to be a horizontal line. So here's my axis, and then I'm just going to graph the line y equals 4. That looks like this. So there's my function. And then this tells me that I'm going from x equals 2, right there, to x equals 5. So that would be the area that we would be finding. Well, what's the distance from 2 to 5? 3. What's the distance from 0 to 4? 4. So what's the area of that region? 12. So we don't really need calculus to do that. But if we wanted to, if we didn't know what the area was of that shape, here's what I can do. I can go under y equals, and I can put in my function. My function is y equals 4. I go to second trace, calculate. Which one do you think we want? Number 7. And then I have my function, and it's going to ask me, what's your lower limit? Well, my lower limit is this lower number, which is 2. My upper limit is the higher number, which is 5. And then it tells me what that area is. And notice it's telling me that that area right there is 12, which is the same thing we got with the non-calculus method. So our calculator can integrate these definite integrals for us. But sometimes we don't even need it. All right, so let's look at the next one. So we have the integral from 0 to 3 of this. So in this case, here's our function, y equals negative x plus 3. So we're trying to sketch the region corresponding to this definite integral. So I'm going to draw my axes. What kind of a shape is y equals negative x plus 3? It's a line with a y-intercept of 0, 3 is my y-intercept, and then my slope is negative 1. Down 1 over 1, down 1 over 1, down 1 over 1. So here's the line we're talking about, and this is the area we're talking about. Well, that shape is just going to be a right triangle, isn't it? So if I think about it, this is going to be my base, that's 3. This is going to be my height, that's 3. To find the area of a triangle, it's going to be base times height divided by 2. And so what's the answer to this integral then? 9/2, right? Or 4.5. If I wanted to check it, I could go to the calculator. I can put into y equals my function, which is negative x plus 3. I go to second trace. I want to go down to number 7. I'm going to tell it my lower limit is 0. My upper limit is 3. And then I can see that it's 4.5, which is 9/2. Okay? All right. on the next one. Do you know what kind of shape this is? If I have y equals radical 16 minus x squared, does anybody know what kind of shape it is? It's close. It seems like it would be the one that goes off like that, except for the x squared kind of changes it. It is a semicircle, actually. Yeah, and if you didn't know that, you could go under y equals square root 16 minus x squared. So here's what it looks like. It's a semicircle. Here's the reason why. If I squared both sides, I'd get y squared equals 16 minus x squared. Bring this over, x squared plus y squared equals 16. So that makes it a real circle. But then if I were to solve this for y, I would have to take the square root. And when I take the square root, I'd have to put plus or minus. So if I just have the plus, it's just going to be the top part. So here's the shape we're looking at. Okay. So we're talking about this area bounded from -4 to +4. We could find this area without using a calculator because this is a semicircle. The area of a circle is pi r squared. So this area is going to be pi times 16, but then I'd have to take half. So this area is 18 pi. And of course, I could also figure it out on my calculator. I don't need to do that. All right, what about the bottom part here? Middle part, rather. Now we're going the other direction. We're given the picture, and we're supposed to state the definite integral that would yield this area. All right, well, the area is going to be equal to the integral from this point to this point. Well, this point is when y is 0, so I would have to set this y value equal to 0. If I solve that, I'm going to get x squared equals 9, so x is plus or minus 3. So I know then my lower limit has to be -3. That lower limit, remember, is always what's on the left. My upper limit is going to be this number, which is +3. And then I'd have to put my function, and that would give me that area. So again, what I did, I had to find out what these points were, so I just set it equal to 0, solve that, I got plus or minus 3, so -3 on bottom, +3 on top. Okay, to find this area with calculus, again, this is where y is 0. So I'd have to take my function, set it equal to 0, bring over my absolute value of x. What values of x such that when I take the absolute value would give us 3? Right, +3 and -3. So this area again is going to go from -3 to +3. Here's our function, dx. That would tell us the area. And see, this area right here, I couldn't find any other way except for on the calculator with that set up. Okay, down here, properties of definite integrals. These properties are very intuitive. That's what I like about them. They all just make sense the way they go. So this one says the integral from a to a of a function is 0. You might think of why that would be true. The integral from a to a would be 0. There's no area. If these numbers are the same, there's no area to be found, so it's just 0. This one's saying that if I switch where the lower limit and upper limit is, if I switch these numbers, then I'm going to have to put a negative out in front because I'm switching the order of them. This one just says if there's some point in between there, I can break it apart. We don't really use this one that much. This one says if I have a coefficient or any kind of constant, I can pull it out in front of the integral. This one says that if I have two functions, I can just do the integral of the first function plus or minus the integral of the second one. All right, so they're very intuitive. I'll show you what they mean with some examples. So this is what we're given. We're given that the integral from 1 to 3 of x squared is 26 thirds. We're given this. The integral from 1 to 3 of x is 4. This one. The integral from 1 to 3 of just dx is 2. We're supposed to do this problem. Well, there's a 12 here. I don't have anything where my function is 12, but I have something where my function is just a 1. So what I can do with this coefficient is pull it out in front. See that? Whenever I have a constant, I can just pull it out in the front. So now I just use substitution. So it's going to be 12 times. Then what's the answer to this? 2. So it's just 12 times 2, which is 24. So we're just using substitution on this side. On the next one, see how we have the 3 here? So I can pull that out in front. So then this answer is going to be -3 times. Then I have to look at my list. Do I have that one listed somewhere? It's 4, so it's -3 times 4, -12. All right, look at letter C. Look at this one. See how we do see the x dx, so we can definitely pull out the 4. We already have a 2, so now we're going to have an 8. But I also have to switch these numbers around. If I'm going to switch them around, what do I have to put in front? A negative. So now it's going to be -8 from 1 to 3, x dx. So now I'm going to look for this. Okay, what's that again? That's 4. So -32. And then on this one, when I have two functions, I'm just going to split it apart. So it's going to be the integral from 1 to 3 of x squared plus the integral from 1 to 3 of 1 dx. I can split it apart anytime I have plus or minus. Now I'm going to use substitution. The integral from 1 to 3 of x squared is 26/3. The integral from 1 to 3 of 1 dx is 2. So if I'm going to add those, I want a common denominator, so I'm going to make this one 6/3. So 26/3 plus 6/3 will be 32/3. Okay, any questions? All right, so once again, you're going to have to be able to go both ways. You're going to have to be able to go from the integral to the picture, from the picture to the integral, and then you're going to have to be able to use the properties. And I did shorten the assignment from what's on your assignment sheet, so you do 13 through 41 every other odd, and then on 53 through 56, you're just going to use your graphing calculator, like I showed you up here, how you could do that. Okay? So go ahead and get that done, and you won't have any work over spring break.